Actually, you'd need all of that and then some to solve the problem of the potato moving through the air with wind resistance. All right? And so again, our velocity. Now it's going to be a function of time, yes? And it's a vector. It's going to consist of two components. The x component, which now will be a function of time because the air resistance is going to hold it back and it's going to decelerate it a bit, yes? Same thing with the y component. Function of time. I and j, you guys are familiar with that? Vector notation? Remember that? Okay? Now, one thing that you've got to note, which makes this more complicated, the drag force is in what direction? If the thing is moving this way, the aerodynamic drag is in what direction? Opposite. Always opposite the motion. So that's also a vector. As time goes on, this thing follows a trajectory. What happens to the drag force? It changes direction, yes? With time, with the motion. As well as the magnitude changes. The magnitude, what you can derive by looking at the airflow around this, including the very thin, what we call boundary layer, you'll study that transport phenomena, is that you can approximate this as some constant times the velocity squared. When you put that all together, in terms of the x component, d squared x dt squared is equal to the sum of the forces, and you crank this in. And notice that this involves both the x and y component, as well as the angle. And then you put it the same thing with the y, and then you add in gravity. What you end up is what we call a nonlinear second-order differential equations that are coupled to each other. Oh man, how are you going to get any answers for that? And are you going to have to build a million missiles and test them all because you can't figure it out? Well, you will be able to figure them out because you will have taken numerical methods. That is going to be a course that will teach you, among other things, approximate techniques for solving linked systems of differential equations and other things, numerically on the computer, using Excel or some of the other packages that we have. You will continue with that in something we call advanced computational techniques. In there, you'll extend it so you can do things like fluids, but also things like solids. So that you can determine, for instance, for that combustion chamber, when the pressure builds up, how much is it going to stretch? And when is it going to pop? Which is what you don't want to do, yeah? Don't want it to pop. And by the way, you should be very careful when you build these things because they do explode. The plastic isn't as rigid as you think. All right? Okay, what else? Let me check my notes because I think I may be done talking at you. Yes. Okay, so let's keep in mind, by the time you're done with the curriculum and maybe into graduate school, you'll be able to work your way from the thermochemistry of the fuels through the thermodynamics of the reaction to the thermodynamics of the heat release and the pressure buildup to the dynamics of the potato moving up the barrel with friction and perhaps some lubrication, and then to finally the projectile motion, including air resistance, so that you can predict before you build anything exactly where that potato is going to land. All right? Fortunately, you guys are freshmen, yes? You haven't taken statics, you haven't taken dynamics, you haven't taken thermal and all that, so you are going to have fun. You don't have to do all that analysis. What do you have to do? Build the damn thing and shoot it a lot. Yeah? And that's the fun part. Okay, I'm going to show you a video, which is what you should not be doing.